video where someone is shown to speak something which they have not said. And friends, we all have seen, how, for example, in our recent elections, there were so many deepfakes where people were shown saying something which they may not have said. And of course, in the US elections as well, now a lot of these videos are coming up wherein people are, seen to speak something which is actually fake. Now, facial performance transfer is one type. The other major type, which is also very common, is called face swap based videos. So let's play this video.
Instead, only try to realize the truth.
What truth?
There is no spoon.
There is no spoon.
So in this case, you see that the identity of this individual, originally there was some other actor, now Will Smith's face has been swapped. And unfortunately, this kind of deepfake is being used quite a lot on social media to troll people, to blackmail people. And with the availability of high quality facial performance transfer generation based or face swapping based apps means that one could create deepfakes which could be used to spread misinformation about medicine, misinformation, let's say, against government campaigns. And even if, let's say, there is a fake video which is shared on social media, it gets viral and is called out to be deep fake within a minute. But given how fast information travels over social media, it may have done damage even though if it is momentarily. The other very interesting aspect of deepfakes is this. Let's say there is a person X, a user X, who is looking at a video of a leader whom they follow, and they come across a fake video. Okay, so they don't know that the video of their person whom they are following is a fake video. But in that fake video, assume that the content which is a person is shown to be speaking adheres to how that person says in the real world. Okay, so how would the consumer react? Because they follow that person, will they now pass off as a fake video which says something which is similar to how the person speaks in real life as real or fake, even if there are visual abnormalities? Or there's another aspect. A user comes across a video where the video is real, but the message of the video is against their school of thought. So they do not align to what is being said in the video. How easy it is for them to now just pass it off as a fake video. And you would have come across these cases as well, right? In social media, where some videos were real, they were being called as fake, and vice versa. So what it really means is we need deepfake detectors at both social media software platform ends and also on devices as well, because once the information is made viral, it is non-trivial to contain the harm which that fake information can do. However, if at the source of upload a video can be tagged as deepfake or AI generated, it can lead to a much more aware understanding from a user's perspective. Now, if you look at deepfake detectors, there is a long body of work. In fact, I was privileged to see what Tapasji's team is doing at C-DAC. I think they're doing some stellar work looking at the visual abnormalities which are there in the media. So if you look at other works as well, we see that from 2017-18, colleagues started using the mismatch between the eye close and eye opening. So if you focus at the eyes of individual where the video is fake, sometimes the otherwise very smoothly eye opening, eye closing based operation is seen as noisy. There could be some mismatches or the frequency could be different. So if you train a convolutional neural network on top of it, it seems to work. Then colleagues also looked at a head pose where if you look at me right now in this video feed, and I turn my face towards my left and then towards my right. Essentially, what happens in the fake case of fake video, if this kind of transition happens, a lot of times this smooth transition between the head pose, the generative softwares, they leave some artifacts. So that's something which we would like to be interested in, catching. Then also a lot of methods, they will leave artifact in the form of different in eye colors. The pupils are different, which is a very rare phenomena. So easy for networks to detect that. Recent works by Farid and his group found that the illumination pattern in the faces that is also uneven, which typically is not the case since the distribution of temperature due to the flow of the blood below our skin maintains a similar kind of temperature across the face. It's not that the left face is way colder than the right face, right? And then there are other classic vision-based approaches using vision transformers and capsule networks for detection. And then, of course, multimodal approaches where if audio is available or text is available, then predicting if any manipulation is done. Now, since we are looking at it from an effective computing perspective, in 2018, we started with a user study where we showed 40 users 3 sets of videos, real videos, easy to detect videos, which are also referred to as cheap fakes, and high quality deepfakes. Now, we recorded their eye gaze, essentially where they are looking at on the screen, which part of the video are they focusing on, and also the EEG data. Now, based on this, we did several analyses. We tried to see if EEG itself of an observer was good enough for predicting fakes. We found, well, up to some level, yes, though the classification accuracy was not very high. But one profound observation we had is as follows. Now, row 1 is essentially the real video and manipulated video of the real video, where the manipulation is done to the facial part, the lower facial part, okay, the lip region. And the second row is essentially showing the corresponding fixations. In other words, where were the users looking at when they were presented this video? When we look at the real video, so this is the real video, and we look at the regions where the fixations are, where the users are focusing, what do we notice? That most of the time the users are focusing on the face of the main actor. However, there's a third person in the background as well. So the fixation goes there as well. This is typically how you will, observe around the world around you. Let's say you're talking to someone, focusing on what they are saying, but still due to your peripheral vision, you are aware of what is happening because momentarily your focus switches, but you come back to the main agenda. Now, if we compare this behavior with that of a fake video, we observe that the fixation is only on the face and fixation is not there on the background. Now, what does this mean? Let's say it's a very high quality fake video. Now, it's possible that the user, when they are observing the video, may for a very short moment see an artifact. However, even if they see an artifact, that doesn't really means that they would guess or they will try to observe or find other artifacts. In other words, the content might be very engaging, the artifact might be momentarily, so they do focus, but that catches their attention. You may have seen this in movies or programs which are foreign dubbed, right? So foreign content, let's say, has an English background. Even if the content is very, very engaging, you do notice that the lip movement is essentially not in sync with the background audio, right? So when I say you notice, that means you observe, but then you unobserve it and you keep on, engaging with the content. So essentially, when users are presented with fake videos of extremely high quality, if there is something which is, far away from the normal, they do observe, even if they do not realize. Okay, so it's exploratory versus explanatory. Now, because we observe these kind of artifacts without sometimes realizing that it's a fake video, this can be used as a premises of designing a neural network which can detect fakes. Okay, so this was our work from 2020, where our hypothesis was as follows. If either of audio or video are manipulated, then we will observe a dissonance, a disharmony between the audio and video, which in some cases could be visible in the form of lack of lip sync, some unnatural or unregular lip movements. Now, this is based on a very classic study done by Tom Grimes at Texas State University, early 1990s. So, Tom Grimes is a psychologist and he is studying the effect of lack of sync of audio and video on the memorability and the cognitive load. Okay, so if they observe that if audio video in an advertisement are not synced, that gives to higher cognitive load because the user notices. And sometimes it's possible that the message which is being conveyed to might not be, reached. So there is a question in the chat. So guys, how do you want it? Should I answer the questions which are coming to me right away, or you would like me to answer all the questions towards the end?
Sir, I think we can continue. We'll go with the questions at the end.
Okay. Thank you. All right. So based on this hypothesis, this is a simple neural network which we proposed back in 2020. It's as follows. You have a video, you divided the video into equally duration audio-visual segments. So let's say this is segment 1. You have a corresponding audio segment. You do the face detection. You leave some region outside of the face as well, simply because in a lot of deepfakes, if there are hairs, there are some transitional effects which can be leveraged on by neural network. Then you have a 3D convolution neural network and fully connected layers. In parallel for the audio, you extract features, and then you have convolution layers. Now, this is what the main part of the network is. During the training, we learn a contrastive loss, and to increase the discriminative power of the individual channels, we have two cross entropy losses. So essentially, either assuming that in most of the audio-visual data at that point, either the video was fake or the audio was fake. So, the channel itself should be discriminative enough to figure out if the video is fake or not. Now, as we are adding contrastive loss between the weights of the fully connected layer between audio and video, what it should do? It should maximize the distance between the audio and video pair where either of the audio and video are manipulated, right? So if there is a reference point, an anchor point, you would like to use that anchor point as the reference and then increase the distance between the fakes. At the same time, you would like to minimize the distance between the audio visual pairs which are not fake. Okay. Now that being the training part, during the inference part, again, you take the audio visual sample, you input that into the network. Now what you do at the 8th fully connected layer level, you simply compute the distance between the audio representation and the video representation. And then you get a distance for each pair and you summate that across the whole video. Okay. Now, if this score, essentially the distance, is above a threshold, then it's a fake video. Otherwise, it's a real video. All right. Now, some bird's eye view results from this method. So last column is our method. This is the area under curve. We compare it with a Siamese network, which appeared at the same time in ECCV, then to vision-based convolution neural network-based methods. Evaluation is done on the standard Facebook's DFDC dataset and another dataset called DFTimid, which is a deepfake version of a very popular yet small-sized audio-visual dataset called VidTimid. Now, when you compare the performance of this method on the DFDC dataset, you see that the method performs fairly well as compared to the earlier works. On the smaller DFTimid dataset, by itself, the method performs very well, but not as well as the vision-only methods. We were quite intrigued, why this is happening. So when we look at the data, we realize that given the small size of the DFTimid dataset, 2 and 3 classification error, samples which are misclassified, 2 or 3 led to this decrease. It's a small size set, so it's kind of, this DFTimid at that point was already saturated. Now, we did a lot of ablation studies as well to understand the structure of the network. And, one finding which we had was that at that point, for example, for the DFDC data set, more than 98% of the videos, they were all video manipulations. There was no audio manipulation at all, right? So that was quite interesting to see, because in the Facebook data set, which is considered as standard data set across the community for analysis, even though it's multimodal, the manipulation is in the video. And I would say from a scientific perspective, the good thing about dataset is that there are 7 methods which are used to do the manipulations to the actor videos. So that means there is high intra-class variation within the deepfake class as well. Now, if you look at some of the predictions, so this is a real video, and what we're going to see is a real video of President Obama, and x-axis is indicating the segment ID. Remember, we were dividing video into segments, and y-axis is the dissimilarity score, essentially the comparison between the audio and the video embedding, which we are getting from the 8th fully connected layer. Let's play the video. Here, high dissimilarity score should mean that it's a fake video. Okay, I'm going to show a fake video anyways in this one. What's interesting about, actually very interesting about this video is that the video is essentially a deepfake. That means the lip movement is synthetically generated, but the audio is essentially coming from a mimic artist. So it's a real audio, but doesn't really belong to the subject.
We're entering an era in which our enemies can make it look like anyone is saying anything at any point in time.
Extremely high quality video, but what you notice is that because the audio video embeddings are not belonging to each other, the score is essentially very high, shows that this is a fake. Okay, now if you compare that with the real video of President, you see that the
Thank you for that beautiful introduction.
score, essentially distance is quite low, right? It's always staying below 1 in this case. Now, that being said, we realize that getting the deepfakes detected where the whole of the deepfake was generated, either audio or video, was quite easy actually. If the face is fairly frontal and you have data in your training set where the deepfake class is generated using method or type of methods for which the test data is also generated from, the task is fairly easy. And you can actually see that in the literature as well, that very large number of methods are now all performing above 95% on the task where the complete audio or video is manipulated. But what's really interesting is that if you think from a perspective of attacker, someone who wants to spread misinformation, there the deepfake doesn't need to be generated for its entirety. So the synthetic data doesn't need to be for entirety. But what can be done is that a few words in a statement can be changed, which can change the whole semantic, the whole meaning of the conversation. Okay. So here is a video. Let me play the real video first.
And Mrs. Doubtfire are two of my favorite movies, so I'm looking forward to seeing what Robin Williams has in store for us.
So the subject, I'll play again in the middle, says here, so says two of my favorite movies.
My favorite movies, so I'm looking.
Okay. Now, if we compare that with a fake video, what we are doing is we are injecting just one word. Okay. Let's see, but it changes the whole meaning of the statement.
Patch Adams and Mrs. Doubtfire are two of my least favorite movies, so I'm looking forward to seeing what Robin
What we have done
Williams
is we simply added, least word in front of favorite. That means text is inserted, audio is generated, and correspondingly video is generated for that part. It is merged, blended within the real chunks, and it is very difficult for the subjects to understand that this is a fake video. We did few studies as well to understand, how well the users are able to figure this out. In a quick study, we found that it's very difficult, and later on I will share some findings from a larger study as well. So then in 2021, we started this work on the task of deepfake analysis as a localization task. That is, well, it's possible that, the whole video is not manipulated, but a short part is, which is similar to an object detection task in computer vision, right? Where is the object? Where is that segment which is manipulated? And here is an example, okay? So let's say in a original video, a subject says, I love ice cream. And then what you do is you change love to hate, okay? Antonym of love. And the statement becomes, I hate ice cream. I and ice cream are real. And the word hate, since it has been replaced with the word love, you add a few segments of audio and video. Now, in the first work, which we call as, the localized audiovisual deepfake dataset, and then of course there's a method as well, which is boundary aware temporal forgery detection method. We created the dataset by optimizing the change in the sentiment score. Okay. So the statement, I love ice cream, has a sentiment score of 0.67, which is positive. Now, what we would like to do is we will like to find the antonyms of the word so that the entire sentiment of the statement, it changes to the max. Okay, so from 0.67 to minus 0.61. Now, to generate this data, what do? We take the real video and audio, we convert it from speech to text, and we figure out using parsing the adjectives, the verbs, and the nouns, and then we choose the antonym, the opposites, for maximizing the change in the sentiment score. Okay. For the words which are changed, we generate the voice. Then we do normalization in terms of the pitch so as to map that to the real chunk preceding and after that fake audio. And then we generate the face in itself. Okay. Now that is going to give you the audio deepfakes. Okay. Now it's possible that you can have the audio deepfakes and the video deepfakes in different combination. For example, here you see the first is where for the word which has been changed, you have the generated video and the generated audio. The second is you can have generated audio for the fake word, but the video is simply the copy of what was there originally, the original video. And the third is you have fake video which is generated from the fake audio, but you let the fake audio, so the real audio, to remain in this. Now, why? The third case is very interesting. This kind of is to give an impression that probably something is manipulated, right? Because the facial movement is not in sync with the audio for shorter duration, even though the audio content is the same. Okay. Now, we did extensive baselining of the method as well. Here is one of the methods. Now you take the audio and video as input. You would then extract from a large scale video encoder, pre-trained encoder, the embedding, and from the audio encoder as well, pre-trained audio encoder. And you add a contrastive loss, again, from the same hypothesis which we had. You add the cross entropy loss to the video frames and the audio frames individually. And we add a boundary matching layer, which is essentially based on that since we are interested in looking at the frames which are manipulated, we would like to have a loss which is essentially aware of the boundary, similar to the object detection IOU based loss. Okay. And then we do the fusion for predicting the segment which has been faked. Now, at the bottom is the macro result for this. MDS is the method which I shared with you earlier, based on audio visual dissonance. And AGT is also a video based anomaly detection framework, because this is the same task, right? Given a video, find the abnormal event. And then BMN is the boundary work which we proposed. So we finally had this I3D based backbone, essentially the video encoder, which is pre-trained on very large amount of data. Now, very interesting thing to note, okay, average precision, average recall. Now, say you take average precision at 75% overlap. That means, let's say you have a input video this long, and within this a small chunk is fake. Okay. Now 75 average precision would mean, let's say your prediction should have at least 75% correct overlap with it. Now, when you observe 75% overlap, you see this is the accuracy of the system. This is the AP, right, which is fairly low. Okay. And if you were to move correctness to 95, again, this is the case that it doesn't really work. And what it really also means is, when you are detecting the correct overlap, localizing, the task is very fine grained. So the method needs to be able to not only have frame level or video level based analysis, it should be able to understand the link between the different segments. So we continued working in this direction. And, as I was saying earlier, that we did a fairly large size study. We had 200 videos where one word was either inserted or it was replaced. Okay. And there were 30 participants. So the participants were asked to do two things. One was, what is the, if the video which is shown to them, is that real or fake? And the second was, If you think the video is fake, then which segments are fake, right? That's the second part is actually non-trivial. So here are some of the methods, the neural network based method compared to the labelers. When you simply look at the binary task of if it's real or fake, the methods, perform far much better. This is like a classification task where the human accuracy was below chance. Okay, so not sure if it's real or fake. If you look at the average precision, then in this case, you see that the performance is terrible for the observers when they have to figure out which part of the video was fake. And this one for efficient VIT, it is at frame level. Even then, it is much better at comparison with the human performance. Now, these three are, your chunk level, like localization methods, they of course are performing better. That being said, we now went one step ahead that rather than changing the word, let's go on a larger scale because if you want to train these VITs and the boundary aware transformer methods, you require far more amount of data. Okay, so we started creating this method data set called AV Deepfakes 1M. So this took a good amount of time in the lab because we wanted to create localization method which could be of at least 1 million sample size. So there were three types of changes here. You do the replacements like the earlier work, but you do deletions as well. And the third is insertions. You insert a new word. And if you compare that with the other data sets, for example, AV deepfake is 1 million, 10 lakhs. The most nearby one, for example, DF platter, I think this is from Mayank's lab. DF platter, that's around 1 lakh. And then, forgery net, this is colleagues from Taiwan, I guess. That's again 1 lakh. So so as of today, of course, tomorrow there would be another larger one from other collaborator or group. This is the largest deepfake detection and localization data set. Now, the process of data creation is as follows. Okay, so you take audio and video data, and from the audio you use the Whisper API to extract the text. Now, rather than optimizing just on the basis of the sentiment score, we thought why not use a large language model like ChatGPT. Okay, so what did we do? Well, we said, okay, so let's say the text which a person is saying in a video is the great songbook. Okay, now we extracted that for all the million videos not million videos, around 400,000 videos, because that's a real video for the speech to text API. And then we use the following prompt. The prompt is you are a helpful text modifier. Your target is to modify the provided text to invert its meaning to the opposite direction. And the operations can be either delete, insert, or replace. And then we put that as a JSON file, and it generates the differences, and it also tells us where the changes are. So it's easily created the metadata. So what was changed and what is the location of that change. Okay. Now coming back, so this is how the text is changed. Okay, so from the manipulated text, we had two types of audio manipulation. One is voice cloning one, and the other is a text to speech one. Of course, those of you who have been working on speech generation and text to speech would know that creating text to speech is a more of a personalized task. That is, for each one type you train one model, which not gives you high quality similarity in terms of how the original speaker speaks, but on the other hand, it's a very computationally challenging job because if you had 100 speakers, you would need to train 100 models. And then you also have a voice cloning based. Now we use a zero shot based voice cloning because from the survey itself, we realize that when you have one word or two words inserted in a long statement, from an audio perspective, the audio just needs to sound like the person. It doesn't have to be exactly like the same, just somewhat similarity, because you have real, you have a few chunks of audio which is fake, and then you have real again. People don't realize, observers don't realize. It's similar to, you're talking to someone on phone, and let's say either you or the other person are moving, are walking, maybe the network quality just go down for a second or two, the audio gets a bit scrambled up, but you don't really think that it's a fake data. It's just, how the quality of network has gone down. Okay, so we have a voice cloning based network, and then we generate the two things. Either we generate the full sentence of the text where a word has been inserted, or we generate the new word only. We wanted to have both of these kind of anomalies. And based on these audio, we take the reference pose from the last frame of the real chunk after which the fake chunk is to be inserted, and we then using talklip would create the face. Okay. Now again, similar thing, you could have fake audio, fake video, or fake audio and video both, right? So this leads to a large amount of interclass variation. Now, when we look at the text data, which we have changed using ChatGPT, this is how the distribution of words looks like when the original text was. So, you could see the words like great, no, love, excited, good, etc. But when you use the large language model to change the statement, the words, so that the whole meaning changes, this is how it looks like. Now the inserted or replaced words are terrible, dislike, definitely, poor, and so forth. Okay. Now, we did extensive experimentation for both detection and localization in this case, right, for this data set. And we realized that, detection methods were still doing very well, especially the transformer-based methods. And the ones where you use large-sized pre-trained backbones, like the I3D backbone. And for the speech, you use wave2vec or wave2vec2. But for the localization task, it really didn't work well, okay, the state-of-the-art methods. And along with collaborators this year, then we also floated this as a benchmarking task in ACM Multimedia. It's going to happen next month. To our surprise, we had around 190 teams from different universities and industrial labs which participated in deepfake detection and localization. Okay, detection. Most of the teams, I won't say most, a large number of teams, their performance was above 80%, and a good number had above 90%. But for localization, the best team had, an average precision of 0.8, which of course is really good. But considering, that means that is the current state of the art 0.8, And if you notice, in this case, the audio and video are not generated from very large number of methods. So if your method is really good in spotting the change in transition from real to fake, it should be able to figure out that it's a fake, right? Just 2 methods for audio and 1 method for video. We can generate a lot more, with a lot more type, but it's just, a practical constraint on how much can be, the changes which you can make, simply because this requires massive amount of computing power. Now, if you look at the dataset further, the dataset essentially is very well balanced in terms of the subjects, and also well balanced in terms of the manipulations. Either it's a full manipulation or it's a fake manipulation. So we wanted that, the methods which are evaluated, they actually are not, in any way at disadvantage, that let's say the validation set distribution and test set distribution are very different. So that would mean, test would act as a very surprise. Now, are we going with time? Okay. So some observations which we had from the challenge. Well, multimodal, very effective. For some teams, audio itself was good enough. So we have a few top performing teams where audio only methods worked for localization. Well, it is kind of intuitive, given that, as I already mentioned, that the transition from real to fake and fake to real, that sometimes gives away that, some data has been inserted. And when I say gives away, it means from a neural network perspective, not from like a human perspective. Then what we are working on in this direction further is we want to have multi-view. Right now, the data is strictly frontal, and that's where most of the deepfake research is. And then when, you would have seen these deepfakes which came up during the elections earlier in the year, there were a lot of fakes which were non-frontal. So it was very difficult to tell from a method perspective if they are real or fake. And then another thing which we are very interested is to have a lot more methods for generation, because, you can have large amount of data, but if there are not a large amount of methods which are used for creating fakes, it doesn't really cover the whole gamut of fakes, so that doesn't help the classifiers which are trained on that type of data for more generalized results. Tomorrow, new method comes in for generation, your state-of-the-art classifier may not simply work because the distribution of trained data is very different from this particular new method generated data. Now, we have been also, because we are working in affect and interaction, we have been trying to see where could be the use cases of the deep fake. So this is one, this made a lot of sense during the COVID time, I would say, when, all of us were mainly using online meetings. So we thought, well, if someone joins as another individual in a Zoom meeting, so uses the generative AI software, takes one photo and joins someone else, then how can we detect it? So, one of the methods we tried to put it on a frame grabbing based tool. So, it grabs the frame from the screen on your device and it will detect the face region for it being fake or not. So here is an example of that. This is a simulated meeting, okay? So I will ask people, to say something one by one and then the tool will analyze. So I call this person, Shreya, and he will start speaking.
Hi, my name is Shreya. My ID number is.
So as she speaks, the system is analyzing, if she is using fake software or not. Then I'll call this gentleman who is using another software.
My name is Vineet and my ID is 2176461.
So in this case, the tool says that the probability is high that the person is using this as a fake, software. So is essentially doing identity spoofing. Now, we are also interested in cross-culture based deepfakes. So, to a novice person like me who is not very well aware, let's say, about the Asian culture, when for the first time I look at these two videos, they look like the same person. Okay, if you notice very closely, they are two different people. So it's essentially a face swap example.
We spoke Japanese at home, ate Japanese food, watched Japanese TV.
Okay, some parts you can tell that they're different people, but on other frames, very difficult to tell. Okay, now what we wanted to study was that, when you have fake data where the observer is from a different culture, from a different language speaking country as compared to the subject in the video, then are they able to identify fakes? And if we use the gaze and the EEG signals, can we identify that even if the person who's observing the video of another person from another culture is not sure, can it be used for classification? Okay, so this is an ongoing work since last year, and I think it will go on for a while because there are so many dimensions when it comes to languages and cross culture. So we found that in the study, 87% of the subjects could figure out a video is fake when the subject was from their own culture. But this accuracy dropped to 71% when you present them a video of person from another culture. And well, I'm seeing a lot of things like cross culture, but this is very much applicable to our Indian scenario as well because we have such rich diversity, right? We have such rich diversity that I won't be surprised that that number for access for someone from, let's say, one state to identify a video of another one from a state which is far away, if that is somewhere nearby this number. Now, when we use just the EEG data and a very simple SVM-based classifier, we find that the accuracy of detection for across the culture, that is 84%, okay? So far more than what the persons who viewed the video gave a feedback that if they feel the video which they're watching is fake or not, but their EEG data was quite on the opposite side. Now, there are so many dimensions to this. We are now, right now working with psychologists as well, because when you're looking at cross culture, it's based on the perception, right? So how do you disambiguate knowledge about culture and disambiguate it from bias and disambiguate it from if it's a real or fake versus observation. The other thing is, deepfakes are mostly related to faces. Well, if you again think from the perspective of someone who wants to spread misinformation, it's not that you have to tell to each node in a social graph the same information or the fake information. You just need to tell it to few of the nodes. And if that node is well connected, it will actually get viral. So in this work with colleagues at Sharjah, we are trying to figure out would it mean for deepfake to go across language and to gestures. Okay, so for example, what do we have here? This person's image, and then we have a driving video, and this is a sign language based scenario, and then we generate another video of the sign language, right? So this is work is again ongoing. We're going to submit it to a journal next week. But what we wanted to understand was that, when you generate deepfake in sign language, right? From the perspective of misinformation, how well are people able to figure out that this is a fake? And then we also asked, sign language interpreter expert to label the generated data because we can't really understand sign language ourselves. To see that if you have sign languages which are methods which are going to create deepfakes where you have sign languages being used for communication, then how well could you detect it? Now imagine in a state address where the main person, the minister, he or she speaks fake, let's say some words are added or deleted or inserted there, and parallel there's a picture in picture where someone is doing sign language, some fake there, some fake there. That would be a perfect ingredient for creating a deep fake. And when it is shared on media, different people will have different perception of it, right? So that's the point. When someone wants to create a misinformation, they would like people to know something which is either not true, or different people to know something which is tending towards their biases. Okay, so this brings me towards the end of my talk. Some learnings: we find that when you use the signals from users, human inspired or implicit, like EEG and eye gaze, they're quite useful in detecting deepfakes. Audio visual dissonance works, but of course it fails as well. When you look at the mismatch between audio and video, and especially if it is a video which is dubbed video from another language, this fails magnificently. So the hypothesis is, which I shared with you, that if audio or video are manipulated, then one of the the audio or video based manipulation would be observed in the form of, let's say, lap uplifting or the unnatural facial movement, right? That is anyways not true when it comes to cross language data where the language is dubbed. Then of course, fine-grained localization requires chunks, but chunk segmentation in itself an open study. We found it's useful, but there are better strategies for sure for that. The other thing is we learned, yes, more data, 1 million data set really works, but more data by itself is not sufficient. It requires a lot more methods to be added to it for creating more generalized detectors. Still, localization is non-trivial. Detection, I won't say detection is a solved task. Detection is difficult, yes. Still difficult, when you mix, for example, fake data class with data where some manipulation, let's say, is done through face swapping or through lip enactment, that type of data with data which is completely 100% synthetically generated, right? So that way, detection also becomes non-trivial. Now you have the fake class, which is very, very different in itself. Now, the other thing is generalization. We can't always keep on retraining data sets. So similar to how generalization is being studied in machine learning problems, we need that in deepfakes as well. We're talking about faces mainly. We started looking at gestures. I think other colleagues are also starting to look at gestures, but there are a lot more scenarios for deepfake. For example, and this goes to classic forensics. You have an image where there are two people who are pointing to the same object, but then what if the object essentially is changed and the gesture is also, where two people are pointing, that is also edited. So it's not just about the subject face or the gesture, it's also about what they're interacting with or what is their role in the scene. If it's a group-based scenario, what is their importance, or who is the leader and who is the follower? And then another super interesting thing is personalized models. We started working on it. Of course, there's a practical limit to how many personalized models, person-specific models one can create. But we think, well, for important people, we need to have personalized models. But again, if let's say you were to train a deepfake detector for a very important person based on their speeches which are available online, it will be a very difficult task because when people speak, generally good speakers, they move a lot, they have a lot of head movement. So creating personalized deepfake detectors, even if a lot of data is available, just by using the same method is non-trivial. It requires a lot of reprocessing in terms of things like head pose normalization. But then I think it's also possible that we may not have to train for each person. There are other strategies which are possible as well. All right, so this brings me to the end of my talk, and this is an acknowledgement to all the wonderful collaborators at different universities and PhD students, and also